Today we're going to talk about centripetal force. We're going to do this using the centripetal force apparatus created by PAFSCO. Ultimately, what we're going to take a look at is how changing the mass or the velocity or the radius of an object affects the centripetal force that is experienced by that object to keep it in its circular path. Here we go. Let's do this. So you can see here that we have a force sensor attached to a thread. That thread is going down underneath a pulley to this rod here. This rod is attached to a motor and is going to spin. This is a movable mass. So what we're going to look at is how this mass affects the force, or how much force is required to keep this mass in its circular path. It could start here, and as it spins, the inertia of it's going to cause it to move outward until the string reaches a point where it pulls back with an equal force that's going to cause it to spin in its circular path. This can be measured, as you can see here on our screen. We have a force that's going to be measured by this force sensor, and we have time. There is a photo gate back here by the object, this post that's underneath here. As it spins through, this photo gate in the back will cause the photo gate to count the period, or measure the period of the rotating rod. We have a mass equal in magnitude on the other side to help balance this off. Otherwise, we get an unbalanced rotation. Helps the motor out. So let's see what happens. I'm going to turn on the force sensor. We're going to tare it, and I'm going to turn up the voltage over here, which will help cause the motor to start to turn. You can see the motor turning, and as this happens, we can see force. According to the equation on the screen here, as the velocity goes up, so should the force. So we are holding the mass constant. The mass that's on there is being held constant. The radius is being held constant. The string length isn't changing. And so if I increase the speed, we can see that the force goes up. You can see the force sensor here is now reading 2 newtons. You can see that it's spinning faster. As I decrease the speed, that force drops. So the next thing that we are going to do is we are going to change the mass. And to do this, we're going to set the voltage to about 4 volts. Over here, that's just the voltage going to the motor. And we can see the period is 0.29 seconds. The force at this point is floating about 0.63 newtons, 63 hundredths of a newton. It's bouncing around a little bit. That's an error in the force sensor itself. As this thing is spinning, there is a little bit of an extra pull, but you can see the value. What I'm going to do now is I'm going to stop it. And we're going to add, we're not changing the length of the string, not moving this. I'm just going to add on here extra mass. Okay, we're putting on there, we went from 10 grams to 30 grams. There's a 10 on there, and I added a 20, so we're at 30 grams. Do the same on this side. All this is doing is helping balance the system. It's again just going to help prevent the system from wobbling. Put this on here. Okay, and now we are going to again turn it on. we're going to line up the period. It's really about lining up the period. Here we're lining up the period so that the amount of time it's taking to go around, we're getting the same velocity at this point. And it is clear that as we adjust this, the force is much greater on the string. There's a greater force because you need a greater force to keep this in motion. The mass out here on the end has a greater inertia, and so to keep it from flying off, the string has to pull back with a greater force. It's clear that as the mass went up, the amount of centripetal force also goes up. Now, the last measurement is going to be the hardest to understand, because as we adjust the radius, we also adjust the velocity. They occur together. We can see this by looking at the equation that you can see on the screen here, that the period, and that's how we're going to measure our velocity. We're going to see the period located right here, that the period goes up as the radius goes up. So as the velocity changes, so does the period in that radius. And so to really understand what we're going to do here, we're going to have to realize that as we double our radius to get the velocity to work out, we are going to have to double the period. So to understand how the force goes down as the radius goes up, or another way of saying this is the force goes up as the radius goes down, we are going to have to really take a look at the concept of the radius and the period, because we're going to be measuring the period in our experiment. And so the period of the spinning mass is going to be the same. We haven't moved the posts. The rod is that's a solid rod. And so the amount of time it's going to take is going to be as this thing spins, is going to be the same. It would be clear that the linear velocity, v, is equal to omega r. So omega is going to be the same. As we go further out, the radius is going to be going up, and so our velocity would be going up as well on the mass. So we're measuring the period in the same spot and getting the period, the angular value, the period for the amount of time it takes the rod to go around. But then we take a look at the velocity, and the mass is out here. We're going to move it in, and that's going to cause the velocity to go down. And the impact then on the force can be seen, because we know that velocity as this thing is moving around is equal to 2 pi r over t. And so we can substitute that into our centripetal motion equation, mv squared over r. And when we do that, we end up with the centripetal force is equal to m times 2 pi r over t, and that is squared divided by r. So the centripetal force would equal 4 pi squared r squared m divided by t divided by r over 1. We would take the reciprocal and multiply, and so that would be 4 pi squared r squared m over t times 1 over r. The r squared and the r cancel out, and so we're left with a nice clean equation of centripetal force is equal to 4 pi squared r times m over t. So without velocity in there, we're able to see that as the period goes down, that the force should go up. And so to measure this in our experiment, we are going to drop the period down to about 14 hundredths of a second from the 28 or 29 hundredths of a second that we just saw. So let's see what happens when we do that, and that will demonstrate that as the radius changes, so does as the radius goes down, that the force itself would go up. And so we'll demonstrate that now. So now we're going to take a look at how the velocity being held constant and the mass being held constant while the radius changes affects the overall force. So to keep the velocity constant, as we've talked about, we need to make sure that we recognize that we have to adjust the rate at which this spins. V is equal to omega r. And so as the radius goes down, to keep the velocity the same, we need to increase the angular speed, which means that the period would have to drop. So by decreasing the overall radius, right now we're at about 9 centimeters. We're going to drop this to about 4 centimeters and see what happens to the force. The period for 9 centimeters was about 0.2928 seconds. So we're going to drop that to about 14 hundredths of a second. So we're going to cut that in half as we cut the radius in half to identify what is going to happen here. Again, V is going to equal omega r. And so we'll bring this in to adjust this. I'm going to move this string upward. There we go. We have it in place. A little bit of slack there. It's into about 45 millimeters, 4.5 centimeters. We're going to turn this on. Again, when we were spinning this previously, we were recognizing, we'll tear it one more time, we were recognizing that the period was about 28 hundredths of a second. So to keep the velocity at this smaller radius, the velocity of the mass, the velocity of the inside mass, we need to decrease the period to about 14 hundredths of a second. There we go. We can see there's a much greater force acting on this at that point. Again, the mass itself, even though its angular velocity is increased, the linear velocity is being held constant there as it was out on the much larger radius. And so it appears to be spinning faster, but linearly, if we were to measure the linear speed of that mass at 45 millimeters or at 90 millimeters, we'd find that it would be the same exact value. More importantly, as the radius has changed and we've kept the velocity the same and we've kept the mass the same, we are seeing a greater force on our force sensor. If you have any questions, as always, please let me know. Have a wonderful day.